Okay, so we're going to start 5.1 today. 5.1 is about areas and distances. So this is kind of the beginning of what some people feel is the harder part of Calculus 1. And then when you start Calculus 2, you pretty much pick up right where this leaves off. So we're going to there's 5 sections from chapter 5 that we're going to cover. And then we're going to try to cover 4 sections from chapter 5 and 2 sections from chapter 8. But we'll see how that goes. We may not have enough time for all of that. So I'll try to do my best to pick the sections that are most important moving forward. So the first thing we're going to do is kind of look at another way that we can talk about area and distance and see a relationship to them. So suppose you are out on a walk at a constant velocity of 25 meters per minute for 1 hour. How far do you travel between time equals 20 minutes and time equals 60 minutes? So we know that this is equal. We know distance equals rate times time is a formula that we have that we can use whenever we need. So without much thought, we can kind of think of this as 25 times whatever 60 minus 20 minutes. So we're going to be traveling for 25 times 40. So that will equal 1,000 meters. Okay, so this is our distance. Distance equals 25 times 40, which is 1,000 meters. Okay, so if we plot this on, if we plot this velocity, we can see graphically what's actually happening. So let's say we make our line right here for 25. And then let's do time is 10, 20, 30, 40, 50, 60. So here's 10, 20, 30, 40, 50, 60. Okay, so I'm going to shade in my graph. So well, you know what? I'll do it like this. So we know that we have a constant velocity of 25. All right, so this is V of t is equal to 25 meters per second or meters per minute. And then I'm going to shade in from 20 minutes to 60 minutes. Okay, now this line is pretty crooked. I should be drawing, oops, oh my goodness. I should be drawing a somewhat straight line. I'm doing my best. And then we shade this in. Okay, so we've shaded this in, and if we were asked to find the area under this curve, what would the area of this curve be? Well, it would be what, 40, because this distance from here to here is 40, and this height from here to here is 25. So what's 25 times 40? That would equal 1,000. So the area, in this case that's in green, of this rectangle that I created with this velocity of constant velocity of 25 meters per minute, if I wanted to find the area of this curve, it turns out to be the same thing as the distance I traveled. So depending on how we graph things, depending on how we deal with different concepts, sometimes area under the curve can mean more than just area under the curve. In this case, it could mean the distance traveled. So that's kind of the key concept for all of chapter 5 and even 6, to be honest with you, is you first learn how to find area under the curve. You learn what it is, how to find it. And then in chapter 6, you kind of learn what it can do. And in chapter 7, you learn what it can do. In chapter 8. In chapter 8, when we're talking about arc length and surface area, you're finding distances and areas. And in chapter 6, you could do anything from work. You could find how much work is being done on a spring that oscillates. There's all kinds of applications of area under a curve. I mean, like, honestly, there's just too many. You could do probabilities. There's just so many different applications. So first we have to kind of take a look at where this all kind of came from. So let's build some concrete examples. These are a little slow and tedious, but I just want to kind of give you guys a rough background on this, and then we can kind of expand it from there. Okay, so let's use 4 rectangles. Use 4 rectangles of equal width of equal width and left endpoints, and you guys will see what I mean in a second, to estimate the area between the curve of, the curve f of x equals negative x squared plus 5 and the x-axis on the interval from 0 to 2. Okay, so we're going to use 4 rectangles. So the first thing I have to do is I have to create this little graph. So you guys know that this is a downward facing parabola that starts up at 5. So 1, 2, 3, 4, 5. So let's draw this guy, and he's downward facing. So it's like that, and it's like that. However, I don't really need that because we're only going from 0 to 2. So let's say that we have, here's 1 and here's 2. You know what, that's not. So let's go 1, 2. I think 2 comes pretty darn close to the end. Okay, and now I'm going to use left endpoints for my heights. Okay, so what that means is I'm going to have, let's see here, f of, if I take this as 1 and this is 2, okay, so I'm going to have these split here. So I could build 4 rectangles, and I'm going to do left endpoints. That's a left endpoint. That's a left endpoint. And that's a left endpoint. Now, I'm just going to be honest with you guys. These are all supposed to be equal width rectangles. I just can't draw. So we're going to use these rectangles, right? And we're going to find the area of this rectangle. We're going to find the area of this rectangle. We're going to find the area of this rectangle. And we're going to find the area of this rectangle. Now, something you guys should notice is that right here, let me get a different color. Right here, this is like an overestimation, right? Because these parts of the rectangle are all higher than the curve. So we're going to have a little bit of an overestimate. So as long as we go into this knowing that we're overestimating, we're fine. And if we wanted to find, the calculations for these, we would call this left endpoint 4. So I'm going to add up these areas, okay? Well, I need to find the first rectangle plus the second rectangle plus the third rectangle plus the fourth rectangle, right? So the first rectangle has a height of what? Well, actually, we know the width, by the way. We know the width of each one of these guys, right? What's the width? The width is 1/2, right? The width is 1/2. The width is 1/2. The width is 1/2. Because we split the interval from 0 to 2 into 4 pieces. So that means each rectangle has a width of 1/2. So what I'm going to do is I'm going to say, well, the first rectangle has a width of 1/2, and what's its height? Well, its height would be f of 0, because think about this. You're right here, right? So right here, this height right here, right there, what's the height of that rectangle? Well, it had to touch the parabola, so its height is f of 0. When you plug 0 in for your x coordinate, what would your height be? Now we're going to do plus. The next rectangle has a width of 1/2, but what was its height? Well, its height is going to be f of 1/2. Because look, what is my coordinate right here? Oops, maybe I should use gray. So my coordinate right there is 1/2, comma, and then we need to find out whatever f of 1/2 is. My coordinate right there will be 1, comma, f of 1. My coordinate right here will be f of 1.5 or f of 3/2, comma, oops, I'm sorry. It'll be 1, comma, f of 1.5. And then let's see, that'll be it. That'll be the heights. And then this guy right here that I wrote in green, I'll fix to gray now. This guy will be 0, comma, f of 0. So those will be my 4 coordinates for the intersection points of my rectangle with their left endpoints. So that means this next guy will be 1/2 width times the height. And again, you guys understand why I'm doing this is because this is just base times height to find the area of the rectangles. And I have 4 of them. So I'm doing 4 little base time height problems, or length times width, whatever you want to call it. This would be f of 1 plus 1/2 times f of 3/2, or 1.5. So when I plug all of this in, you guys should get 1/2 of 5, because if I plug 0 in, I get 0, plus 1/2 of f of 1/2, so that would be 19/4. And you can just plug this in your calculator. F of 1/2, next one would be 4, plus 1/2 of f of 3/2 would be 11/4. And when you add all these up, L equals 33/4, or 8 1/3. Okay, so that would be our estimated area, and it looks like it's an overestimate. Okay, so now we could do the same thing. Okay, so we're going to do the same drawing, and again, I'm doing my best to make it the same. So this will be 1, this will be 2. Okay. And I'm going to try, but this time I'm going to do right endpoints. So I cut here, I have to cut here. So this time the right endpoint starts here and goes left. We go up here, the left endpoint goes here and goes left, left, that way. So this time, these little gray intersections right here that I drew, maybe I should do blue. These little intersections right here, these all intersect with the right endpoint of the rectangle and the parabola. So now I'm going to do R4. This would be right endpoints. Okay. So 1/2. Now, what is the height of this first rectangle? Well, it would be f of 1/2, whatever that height is when I plug half. Then the next one is 1/2 times f of 1. The next one is 1/2 times f of 1.5, or 3/2. And then the next one is, 1/2 times f of 2. Okay. So when you plug all this in, let's see what we get. So I'm going to take, and if I plug 1/2 in, I should get 1 times 19/4. When I plugged 1 in last time, I got, so this would be 1/2/4, or times 4. The next one's plus 1/2 times, I said I got 11/4. And then the next one, we just put 2 in. So I'm going to put 2 into here. So that would be 2 squared is 4 with a negative. So we should get 1, okay? Because -4 plus 5 would be 1. So we'll have 1/2 times 1, okay? So now this should be 19. You know what? I'm just going to do this 19/8. I'm going to factor out the 1/2. And this will be 19/4 plus 4 plus 11/4 plus 1. Let's see what that is on our calculator. 19 divided by 4, or 11 divided by 4 plus 1. So I'm going to do math frac, and then I'm going to multiply this times 1 divided by 2, and we get 6.25, which is 25/4. So we get 25/4. So this is 6.25, and this is 8.3 bar. Okay. So you don't know the correct area, but you do know that it's somewhere between 8.3 bar and 6.25. So some students would even try to average it out. They might try to say, well, what if we added these two up and then divided by 2? That should be the area. It doesn't quite work like that. If it was linear, that would probably work, but this is parabolic. So the behavior isn't quite symmetric how you want. So it might be a close estimate, but it will not actually be right. Okay, so this is what left endpoints and right endpoints mean. You could even use midpoints. There might be one in the homework that I assigned where it uses a midpoint. So then you take the halfway point between 0 and 1/2, so you'd get 1/4, and then so on and so on. You take all the midpoints and use them to create, and that would be called M4, and you'd use that to create your rectangles. Okay. Now, the idea behind this, okay, is what if I had this curve? So what if I had some curve like this? Okay. So let's say I had some curve like this, and I use this situation here. Okay, so I had this curve, and I wanted to approximate the area under this curve, and let's say that this endpoint is A, and let's say this endpoint is B, and we're going to go from A to B. Okay, and we're going to use, let's say, right endpoints with n equals 5. And by the way, right endpoints is kind of the arbitrary way that people do things in these situations. You could technically use left endpoints if it were a different book or something, but in general, I've seen most people use arbitrary right endpoints. Okay, so that means that, and we're going to make 5. So here's 1, 2, 3, 4, 5. Okay, so I don't know if I drew it quite perfect. Maybe I should go to like there. Okay, so we're going to go up to here, and we're going to do a right endpoint. Okay, then we're going to go from here, and we're going to do a right endpoint. Then we're going to go from here, and we're going to do a right endpoint. Okay, then we're going to go from here, and we're going to do a right endpoint. Then we're going to go from here, and we're going to do a right endpoint. And again, you guys, you understand these are supposed to be symmetric. I just can't draw. Okay, so what if we wanted to now use, oops, let's use red. Now use n equals 20. N equals 20 for this. Well, first let's look here. So this A would have been my x sub 0. This would have been my x sub 1, my x sub 2, my x sub 3, my x sub 4. This would have been my x sub 5. Okay. So whatever n is, that's how much you do the distance. So you would normally say B, this thickness right here, is B minus A divided by N, right? So however many ways you cut it, you take the distance from one end to the other end of the graph, and then you divide it by how many rectangles you're making, and you'll find out how many equal width rectangles you're creating. So if we use 20, I mean, I'm not going to go through and draw all 20, but you know, let's say that this was the midway point, and this, and this, and this, and this. You guys get the idea? So I'd be doing this. Oops, I messed that one up. I don't even know how many this is anymore, guys. Oops. I just lost track. I got kind of sloppy. You guys get the idea, right? So the thing is that which would be more accurate, the rectangles of red or the rectangles of green? The rectangles of green would have some error involved because there's some overestimation, there's some underestimation. You're not quite sure which is greater. But the rectangles in red, you're going to have some estimation and some overestimation, but they'll start becoming more accurate. What if we wanted to use 100 rectangles? How accurate would we be? I'd feel like we'd be much more accurate because all those little overages or under estimations, they'll start becoming much smaller values because you can cover more parts of the curve. Now change your thinking. What about 1,000? What about 10,000? What will eventually happen is you'll just start doing this. You'll just start building these, and you'll just start having rectangles that are so thin you can't even see the distance, the width, and you're just going to start having all these lines. They won't be rectangles anymore. They'll just be lines with or rectangles infinitely thin. That's what ends up happening as you start approaching an infinite amount of rectangles. So our goal is to translate this from 5 or 20 or 100 to the idea of an infinite amount of rectangles, but you could never actually draw an infinite amount of rectangles. So what's the only way in calculus that we can kind of deal with calculations with limit? Or I screwed it up, I said it. The only way we can deal with doing calculations with infinity is we have to bring limits in, okay? So we're gonna be working with limits in this course. It's a little bit harder to explain in all of this online. So what I'm going to try to do is I'm going to try to kind of jump ahead a little bit. This is the idea behind it. We would like to be able to talk about an infinite amount of rectangles. Okay, so we need limits. Okay, so I'm going to show you guys something called the Riemann sum. Okay, and basically what we're going to talk about is the distance from here to here, or from here to here, or from here to here, or any of these those distances are called delta x's, right? So if you took all the delta x's and added them up, that would be the total distance, okay? So when we're working with these problems, delta x is going to equal b minus a over n. That is how you'll find what delta x is, meaning the thickness of the rectangles, okay? And we want to sum all of these rectangles up. So what we're going to do is we're going to also recognize that x sub I, so x sub some interval, or some sub, is equal to a, and this is a subscript of I didn't write it very well, is equal to a plus I times delta x. And if you don't believe it, you could just come over here and do x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. Okay, and if you started off right here at a, your x sub 0 would be a, right? But then don't you add a delta x to get to the next rectangle? And then the next one would be 2 delta x's you've now walked. The next one would be 3 delta x's you've now walked. The next one would be 4 delta x's you've now walked. And the next one would be 5 delta x's you've now walked. Okay, so and you could say that this goes down to any x sub I. Well, that's going to equal a plus whatever interval you're on. How many rectangles have you walked over? Well, I have walked over I times delta x rectangles. Okay, so these are the two kind of things that we need. What we're going to be working with is the Riemann sum. So the Riemann sum then takes all of these ideas, these rectangles, but it doesn't just use rectangles. It could be many things that you add up. But this idea behind it is it says that the exact area A, so again, right now, these are estimated areas, right? But what if we had an infinite amount of rectangles, they would no longer be estimates, they would be exact. So that's what we're trying to work with here. We're going to say the exact area A between a curve y equals f of x and the x-axis from x equals a to x equals b is given by this. A equals the limit as n approaches infinity of the sum of all of these rectangles. So that'll be I equals 1 to, oops, not to infinity, to n. I equals 1 to n of f of x sub I times delta x. Now, what is the f of x sub I? Well, we come up here. Wasn't this always my heights? And then what was this? These were always my widths, okay? So what we're doing is we're taking this base kind of way we did it, and we're translating it into an infinite amount of them. Notice that it says n is approaching infinity. So this is saying we're gonna sum up an infinite, near infinite amount of rectangles. This is the thickness, this is the height. So you're doing base times height, base times height, base times height, base times height. How often? To the end of time, till you could possibly, as far as you could ever imagine, okay? The infinite amount, okay? However, this must be true, oops, and this must be true. So where delta x equals b minus a over n, and x sub I is equal to a plus I delta x, okay? And something big, f of x must be continuous. Okay? So we have this situation, and basically this is kind of 5.1 and 5.2. I kind of want to show you guys what you can do with this. So let me see how bad this one is. So yeah, let's try an example. It says express, by the way, this right here is the limit of the Riemann sum at infinity, okay? So the summation is called the Riemann sum, and we're taking that limit at infinity, and that's going to give us something special, okay? So it says express the area between the curve y equals x squared and the x-axis on the interval -1 to 2 using the above definition, okay? Or the infinite Riemann sum, the limit of the infinite Riemann sum. Okay, so first we need to identify my A. So A equals -1, B equals 2. So that means I know my delta x is equal to 2 minus a minus 1 all over n. Okay, so that means we end up with 3 over n. Okay, then we need to identify my x sub I, but I told you guys that x sub I is a plus I times delta x. So our a in this problem is -1 plus I times delta x, which is 3 over n. So that means my x sub I is equal to -1 plus 3 I over n. So this is my x sub I, and this I is a subscript. It is not the imaginary number I, okay? This is just a subscript. You could have called it J. Some books use J, some books use K, whatever it is. Okay, so we have my delta x and we have my x sub I. Now, is x squared a continuous function? Yes, it is. So we're going to try to mess with this a little bit. So we have a formula that says area equals the limit as n approaches infinity of the sum I equals 1 to n of f of x sub I times delta x, right? That's our formula, okay? So let's plug in what we know. So what we know is the limit as n approaches infinity of the summation of I equals 1 to n. Now, f of x sub I means that whatever x sub I is, you plug it into f of x. So f of x is x squared. So I'm going to take -1 plus 3I over n, and I'm going to square it. And then it says multiply by delta x. So I have times delta x, but what was delta x? Delta x was 3 over n. So once again, here's my delta x. That goes right there. Here's my x sub I. That goes right there. So now we got a little cleanup to do. So area equals the limit as n approaches infinity of the summation of I equals 1 to n. And I'm just going to FOIL this out. So this will become 1 minus, what is that, 3i 3i over n plus another -3i over n. So that would be -6i over n, I believe. So let me write that. -6i over n. Then we have to square this, so this would be 9I squared over n squared, and all of that times 3 over n. Okay, so that would technically be the problem, right? So we've written it out. However, you know what? I'm going to say that's going to do it for this one. I'll show you guys how to expand this in the next problem. Let me see if I got it for you. Yeah, I'll have to expand this in the next one. So this would be, so it says express the area between the curve and the x-axis using the above definition. So we've expressed it. We've done our job. This is not normally the final answer, but we don't have all the tools to deal with this. We don't have everything to deal with the I and the I squared. So we're going to get to that in the next section. I could even clean this up if I wanted to simplify. I could say A equals the limit as n approaches infinity of, the summation 1 to n. So this would be what, 3 over n minus 6, not 6. This would be what, minus 18I over n squared plus 27I squared over n cubed, right? So that's just me distributing the 3 over n to everything. Okay, so we have this, all right? And tomorrow, or I'm sorry, not tomorrow, but in the next video, I'm going to go through and actually find the calculations for this limit. Because right now we have i's and we have n's and we only know how to deal with the n for the limit. So I'll show you guys how to do that in the next section in 5.2. But this should be good enough to get you guys through some of 5.1. All right, everybody, that's going to be it for this video.